Myself, my name is Michael Jarret. I am, first of all, I'm the Associate Director of QSEC as of a month ago or so. And I am also an assistant professor in both the mathematical sciences and the computer science department here at NISA. And so today, I'm going to be giving you an overview of quantum computing. What is it, in general? Why should you care? And also, what's going on here at Mason, or at least a sampling of some things going on here at Mason. Maybe not going to exhaust every single bit of research. So this is not working. Thank you. What did you do to me? All right. So let's just talk about what quantum is, the state of the field, where things are at, where they're heading. So quantum technology, it's not just the future. Like, we talk about it as if it's this thing that's coming, it's about to be here. It isn't here yet, but we're going to have it soon. And that's true. But there's more to the picture. So right now we've got quantum computers hitting the market. And by hitting the market, I mean, not for you guys to play with. Well, you can play with them, but not for you guys to use for anything that you might care about in your regular lives, but for researchers to play with, for people in industry to attempt to use for various computational problems that they might be good for the industry to kind of figure out where things are headed, right? And that's the nature of quantum computers in industry presently. But quantum technology has actually been around for quite some time. So, for instance, we've been using MRIs since the 70s. And the MRI is based fundamentally on quantum mechanics and quantum properties. And it used to be called nuclear magnetic resonance imaging, but they got rid of the word nuclear because I think it scares people or something. And they just called it magnetic resonance. But these things have been around, they're here, we have them. And our interest in them is only growing. So what does this mean for, technology, society, the workforce in the future? So first off, we've got some limited purpose, but powerful devices. What do I mean? We'll see more about what I mean by this in a minute, but we're going to have some computers that can do things in domains that are relevant, but where the end user who just cares about their GPS system or I don't know, Snapchat or whatever people are into these days. I guess I'm aging myself or dating myself. Might not really notice, right? If people like me do our jobs properly, then the average person probably will not really notice that much has changed about their lives other than maybe some things got a little faster, a little snappier, something like that. But it's mostly going to be in the background. So some domains that these computers, at least right now, we believe are like cryptography. So we know this Shor's algorithm is a big thing that came about in, I don't remember whether it was the late 80s or early 90s or whatever, but it broke all public key encryption schemes that are presently used. There still are such things that we don't know. One of the other conjectured ways that a quantum computer might help the world is through drug discovery. And I'll talk more about why you would believe that in a second. Or actually, let me get to it before I even continue, because I'm on it right now. There's this, quote from Richard Feynman from however long ago. I don't know when he actually said this, but he was asked, I think, something along the lines of, what is a quantum computer going to be good for? And his claim was, well, nature isn't classical. And so because the world itself is fundamentally quantum mechanical, if you want to actually make a device that can simulate properties of the world, that can help us understand the way nature works, that device should operate on the same principles that the world operates on. And you can probably leverage more power out of that. And so drug discovery, because we're dealing with small molecules, right, and chemistry, things that obey quantum mechanics, probably needs to be studied, with a quantum computer as opposed to with a classical. Also, there's some belief that maybe these machines will be good for optimization. We don't have all that much in the way of proof of this, but it's an active area of research. And, in general, if I had to capture what it is that these devices will be the best at, it's probably going to be specialized, scientific computation type tasks, which you can kind of imagine all of the things above other than maybe cryptography, unless you really want to shoehorn that in there, are categories that those things fall into. Right, this stuff about simulating systems, understanding their physical properties, etc. But quantum technology in the form of sensors, which we heard about yesterday, also can do things like give us better microscopes. So we can use like quantum tunneling to probe, microscopic things. And, all sorts of other instrumentation based on the properties of quantum mechanics in the laboratory setting, or even in, if I know that this is used for satellites somehow, but I don't fully understand. I'm not a scientist. And the advent of quantum technology, one of the major changes that we're going to see in the near term is we're going to have to change cybersecurity, our own cybersecurity. And NIST, the National Institute of Standards and Technology, is presently even, working on new standards that we're going to have to shift to protect ourselves against possible quantum attacks at some point. Okay, so we can talk about some different research trajectories, but today I'm not going to be discussing metrology and sensing. One, because I am not the person to discuss it, but also two, because today is the quantum computing day. And quantum communications kind of falls somewhere maybe in between the two with overlaps in both, but that is also not something that I'm going to be hitting on. And that's probably fine for everyone in the room because you all came to hear about quantum computing anyway. All right, so what is research in quantum computing and what does it look like? Really, it falls into two sort of things. I broke it out into four. So you have hardware and software, just like regular computing. But presently, you've got real hardware like physics, laboratory stuff, like stuff, you have an optical setup and you play with some lasers and shoot them at things like Patrick likes to do. You have software. And so that presently I'm separating out from the other two. And what I mean by software is, the programming and stuff like that you actually want to just program your machine to use. You have algorithms, and I broke this out because presently, research into quantum computing, especially in algorithms, takes place largely at the level of mathematics and, real theory work. It's starting to change, and we're starting to shift also towards applications where we're trying to create algorithms that work for problems of industry and, academic interest. Obviously, I'm biased towards academic interest, but companies are getting interested. Okay, so what is the history of quantum computing? Unfortunately, that minimized thing here is overlaying. So this is dated by, I don't know, a few years now. Back in '81, Feynman, who we just saw, proposed, the idea of quantum computing. I don't know if he was the first one to propose the idea, but he was certainly the first person to popularize it, I think. And in '85, David Deutsch showed an algorithm. He discovered an algorithm, or not an algorithm, a universal model of computation based on quantum physics. But between 85 and 94, not that much happened that would have been that exciting, but 94, Peter Shor comes around. And this is when things really sort of started getting because Shor came around and showed that, oh, if you had this quantum computer, you could break the majority of modern cryptography or public key. And then, since then, we've been having sort of these landmark things. Most of these are pretty experimental. In 2017, we finally had Google's quantum computer show up, IBM's quantum computer. And in 2019, we had this really landmark result where Google declared that they built a machine that achieved quantum supremacy. And what quantum supremacy was the result that they came up with a problem that a quantum computer could solve that no classical computer would have been able to tackle. Right? It was a very crafted problem. It's very contrived, and it was just done for the sake of showing that their machine was that much more powerful than a classical computer. But at least to date, we don't have any practical uses for the machine. We're still trying to scale up. All right, so this is from 5 years ago, or something like that. And this is from a paper by John Preskill. And it kind of showed where he anticipated quantum computing would be in the next 5 years and then beyond. And this has proven to be fairly accurate. So right now, we're 5 years in from this prediction, approximately, and we're still in this era here known as the disk era. And this is these are these devices that Google's creating, IBM's creating, all these different companies are creating. They can do quantum things, they exhibit quantum properties, but they're noisy. They're not perfect, they're not error corrected. Your classical computer, you don't expect that if there's, a stray magnetic field or, a bolt of lightning or something outside, that your computer is going to just get your computation all wrong. You kind of expect that everything's going to work out perfectly well and fine. This is not the case with these noisy intermediate scale things because your classical computer can do something known as error correction. And we can't do that yet. But within 5 years, which is still where we are right now, the prediction was that we're going to emerge and start having limited, not that many, not that much scale, fault-tolerant quantum computing. And the idea is that at this point, you will have devices out there that can exhibit error correction, that can do these, protective protocols and implement algorithms more reliably. And in fact, we've seen a number of results in the past, let's say 6 months or so, maybe a year, where people have been able to achieve some amount of error correction. But the main barrier now is that we need to achieve error correction at some sort of scale for practicality or for utility, however you want. All right, so now that I've blabbed on about the state of things, it makes sense to describe what a quantum computer even is and how it's different from a classical computer. And I'm sure you've heard a lot of people say a whole lot of things. I'm going to be another person saying a whole lot of things, but I'm going to hopefully give you a pretty decent idea of what's going on that makes it different. So your classical computer relies on something known as a bit. And a bit is just either a 0 or a 1, right? You have some piece of memory or whatever that you can have, a 0 or a 1, true or false. You could also have a probabilistic computer. In a probabilistic computer, you'd have a certain probability of 0 and a certain probability of 1, but you don't necessarily know what's certain. And I think a lot of the time, qubits, the fundamental unit of quantum information, gets a little bit confused with probabilistic bits. But that's not quite what it is. A qubit is basically a vector that points from the origin of the sphere to the surface of the sphere. And it can be any vector, but it is always specifically one vector, which is going to have some weird and funky properties. Now, this means that they can achieve the value 0 by pointing up, can achieve the value 1 by pointing down, but they can also achieve other values that can only be represented mathematically in what's known as a superposition of 0 and And we'll see a little bit of that in a second. All right, so how do quantum computers work? So one of the important properties about them is they don't work the way your classical computer works. All right, so your classical computer, you're used to thinking of stuff like the OR gate over here. Logically, you have a 0 and a 1, or a 1 and a 1, or whatever coming in, goes through the OR gate, and out you get a 0 or 1. Right? You have 2 wires that come in, output, you get 1 wire. Fundamentally, quantum computers are also reversible. And this is a very important property that distinguishes them from what you're used to thinking about. Now, for instance, take a look at the XOR. Without this top wire over here, you just have the standard XOR that you're used to thinking about. But with the top wire, you've carried along enough information to make it a reversible XOR. That means that not only can you run the operation forwards, but you can undo it. And this is going to be a fundamental property of quantum computation as well. And the corresponding quantum gate is known as the C node. We don't have to worry so much about what that means, but unitary operations, those things that map us around that sphere that we saw, are all reversible operations, right? And reversibility is not a property that probabilities, like you flip a coin, you either get heads or tails. You can't undo that. So this is fundamentally different. All right, now another thing that gets kicked around a lot when we're talking about quantum computing is this concept of superposition, which I just mentioned. Things can be either part 0 or part 1. And this is, known or not known. You've probably seen Schrodinger's cat, or at least seen it on TV or heard about it, right? You have a cat, it's in a box, and this poor cat is in the box with some poison. But until we open the box, the cat is both alive and dead at the same time because no measurement has been made. So, the measurement happens when you open the box, and so this cat is quantum mechanically simultaneously alive and dead with no determinate state. And in fact, there's one more concept I want to throw at you, which is interference. And I feel like this one gets dropped from the discussion of quantum computing way more than it should. So this is actually interference. If you had to choose something that makes quantum computer tick, it's this. All right. Maybe in high school physics or college physics, if you had it, you saw this single or double slit experiment where you shine some light into what is known as diffraction grating, and then you get some weird pattern on the wall that we call an interference. Now, the question, I guess my question is, how do you measure? Does anyone know how you measure the interference pattern? You look at it, right? What are you seeing when you look at the interference? So when you look at the interference pattern, you are not seeing a single light wave. You are seeing millions and millions, or I don't know, Patrick, of photons that have hit a screen, right? And they're, you're seeing the reflection of them into your eye, or you're seeing a photograph effectively of where they were, right? You're seeing many, 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 many measurements that have taken place. So you've done the Schrodinger cat experiment over and over and over and over and over a ton of times, right? And this is what you're seeing as the result. But to build up this pattern, you're getting hits of individual photons, like on a screen. And this is where we get to how quantum computing works. So you'll often hear the concept of quantum parallelism. So what is quantum parallelism? Well, in a serial computer, one of the things that you can do is, you can just, suppose you want to try opening a lock with a key. You take a key, you turn it, that didn't work. Try the next one, turn it, that didn't work. Try the next one, turn it, that didn't work, right? Parallel computing, maybe you can exploit resources and try to turn a whole bunch of keys in many copies of the same lock all at the same time and see which one worked, right? Now, quantum parallelism So this graphic, don't take it too seriously. I stole it from somebody's website. You can sort of take a bunch of keys and try them all in the same lock at the same time. So you can do this parallel thing without making like a ton of copies of your lock. And that's kind of the secret sauce. But now one thing that's missing here is that after you try them all, you can only get back a little bit of information. You don't get like a yes or no answer, like this is the key that worked. You get a little bit of knowledge every single time. So you still might need to repeat your experiment over and over and over, just like the diffraction grating, to actually learn which key had opened the lock. That said, the number of times can often be one or many, but where many is much less than your classical computer. And this is basically where your quantum computer is going to get its power. All right. One other property that I've got to throw out there because I'm talking about quantum computing is entanglement. And this is basically just this weird thing where if you've got two bits and they're both in an indeterminate state, it is possible that if you measure 0 on one, you're guaranteed to get 0 on the other. And if you measure 1 on one, you're guaranteed to get 1 on the other. So this is another quantum phenomena, but it's not too relevant today. I just have to say it. All right, so who is presently working in quantum computing aside from us here at Mason? We've got a whole bunch of enterprise companies and end users. So you can see that this is like a big push, a big investment in industry. This could really be groundbreaking for a lot of different industries. All right. Now, focusing more on Mason, this is, you probably saw this yesterday if you were here. If you weren't here, it's back again. So you can look at it now. We've got a center with a lot of people and, I can't quickly count that high. I think Patrick said something like 31.
Yeah, 32 actually.
32. Okay, we're up to 32. And we have groups, materials, which is, stuff you heard about yesterday, and sensing, which you also heard about yesterday, computing, which is a little bit smaller and new, but we're growing. We're still relatively large. And then the education team, which, you will hear about today. All right. So what kind of research does computing do here at Mason? We do work in a few different areas. Algorithms, compiling, machine learning, quantum simulation algorithms, classical simulation algorithms. And so the distinction here is that when you have a quantum algorithm, you want to know if it's any good. The best way to figure that out is to try to create the best possible classical algorithm that can compete with it. Sometimes you can get one that's competitive, in which case you don't want to spend the money on a quantum computer for that problem. Some complexity theory, I think. I believe we have some people doing post-quantum cryptography, and we definitely have a lot of people interested in these NIST devices, actually seeing what you can do with existing industry technologies. So here are some specific examples of the research we do, largely biased towards myself because I had to prepare this talk. I sometimes investigate quantum walks, which are analogous to classical random walks. And they can do things like give you exponential speedups on fundamental computer science problems, such as Boolean satisfiability. So if you're a computer scientist, that is one of these fundamental NP, depending on how you specify things, whatever problems. Okay. Another thing that we've been looking at recently is simulating quantum systems. So this stuff like drug discovery, chemistry, and so on. And I'm going to speed through stuff in a second. And that takes place both at the theoretical level in the math department and also more at the level of practicality with NIST devices, in places like the chemistry department and what have you. We've also got some people playing with these NIST devices and trying to run things like quantum machine learning on things like IBM Q. So there were a couple of posters yesterday, I believe, from people working with IBM Q. So we've got that going on as well. So what do you as a student or an arbitrary person, whatever you happen to be, really need to get involved in this area? Well, you just kind of need some linear algebra and maybe a strong STEM background, but that's it. So that's all we got, right? That is literally all you need. You can go ahead, you can get started with quantum research. So suppose you actually wanted to get a more formal background. We presently here at Mason have 2 dedicated quantum courses, and that's in principle increasing. Those include Introduction to Quantum Computing and Quantum Algorithms. These are not necessarily dependent upon one another, but if you are interested in these things, please come talk to me. And we also have our ongoing quantum computing seminar series every Monday from 12:30 to 1:30 in exploratory hall. All right, but you know, there are a lot of different things that you can bring to the table if you're interested in quantum computing. And you could, you know, get involved in this field from many different angles, taking many different courses, you know, what have you. I'm not going to get too into detail about everything you could be learning. But wait, there's more. You know, and you know what? I'm running out of time. There isn't more. Let's just jump to the end. So thank you. So any questions on quantum computing here? Yeah.
So going back to that slide where you were showing.
Which one?
The slide where you were showing the test methods.
Yeah.
But with keys. Yeah, so that's so then in that case, it's just safe to say that like a quantum computer in their current state or single thread.
No. Wait, what do you mean by that?
So single, they're not truly parallel in the sense that like it's like a
Oh, I see what you're asking. I see what you're asking. You're asking if quantum computers presently, if this many keys in the same lock sort of thing is a single thread sort of operation. The answer is yes. There is some work I think that's been done about, you know, putting quantum processes in parallel with one another and exploiting that. But it's not, I don't think it's that active an area of research, largely because you're gonna get many of the same improvements you get out of classical parallel computing in that case. But putting things in parallel is a fundamentally classical process, right? So you might be able to exploit this, but you're exploiting classical processes to do, you know, quantum algorithmic things, which is something else entirely. However, whatever order.
I go first. So currently, there doesn't appear to be any quantum computer which is competitive in terms of computing power with state-of-the-art classical computers. But there is great confidence that in a not so distant future there will be.
Mm-hmm.
Where does this confidence come from? Is there a theoretical proof that we're not going to hit some unknown physical hurdles?
No, I mean it is possible that we will hit unknown physical hurdles, of course. I would say that it's improbable, however, given the present rate of progress. I think that, you know, most of the confidence that this is coming is largely from the perspective that we have made incredible strides in the past X number of years, right? And it's kind of an accelerating curve. It's not like slowing down. So, you know, yeah, maybe we're in some sort of exponential portion of a you know, one of those curves that flattens, you know, plateaus. But I don't think anyone believes that's really the case.
So there are multiple technologies to realize Which one?
Don't ask
By
me.
yourself.
I am a theorist. I work in the abstract. I am agnostic to the hardware that will work out. And you know, if you talk to any decent researcher, they're going to tell you that their hardware that they work with is probably the one that's going to win, right? They're going to tell you that their model is the right model. And I can't say. I just simply wouldn't touch that question. I don't know, Patrick, do you have a?
I mean, I don't think there's necessarily one that is a clear winner at this point. It just depends who is going to be able to scale up the fastest. And scaling up is non-trivial. It gets harder and harder. It's not like you entangle 5 and you solve the problem. It gets more and more difficult to entangle more and more together. Again, I'm not a quantum architectural person, but what I will say is that it's exciting to see this level of progress where even when I was doing my first bit of quantum computing research back at the Naval Research Laboratory in 2012, it was still a time where everyone just had 1 qubit and they would do 1 operation. And it was a big deal to have 2 qubits interacting and manipulate them simultaneously. And everybody had a 2-level system and could manipulate it. So the fact that we have multiple different computing approaches using different types of hardware and all are showing some signs of success is potentially optimistic. It's also potentially pessimistic in that maybe they'll all run into the same.
I guess I
problem.
would just
But-
throw on that I think the most common technology present is probably superconducting qubits, but that's just a matter of where the knowledge was.
Yeah, I mean, there's the superconducting systems are probably, well, and the IonQ systems are very competitive too. So I mean, trapped ions and superconducting are probably, I guess, state of the art right now. There are other permutations that use actual material properties such as topology to make.
There's photonic, like there's.
And there are different kinds of quantum systems, right? The photonic computers, at least the Xanadu one, don't do gate stuff, right?
I think they simulate everything. I think the intention is to simulate gates at some point,
Okay.
even if you're not implementing them directly.
Yeah.
So as you're doing your research into these different things, are you doing things that are in the like simulating a quantum computer on a classical computer? Or are you actually executing
That's
what's
a
your
very good question.
process?
Yeah, that's a very good question. So me personally, the answer is, you know, as an algorithms researcher myself, I don't have a workflow like you're describing. But there are researchers who their bread and butter is simulating quantum systems with classical computers. And so sometimes I will do research that involves simulating quantum systems with classical computers. Mostly though, what I'm attempting to do there is prove that the quantum computer is not that great in this particular instance. Most of the time though, I'm just on a whiteboard trying to figure out, you know, what is a good, assuming we have, you know, whatever resources we have in whatever model, you know, what is the best algorithm for doing X, or what is, how do I achieve a scaling advantage at, you know, out of particularly fine tuning things. But I also will do some research in, for instance, right now, this compiling stuff, trying to compile quantum computers, right? Because you're going to have some architecture, you need to compile it down to their language. And in that case, we are literally simulating the quantum processes on the classical computer to try and figure out what the best compiling algorithm is. But the classical computer kind of can only do this for so long before it chokes, right? You know, you have so many quantum gates, and by the time we're only dealing with 2 qubits in this research, and by the time you get down to 8 gates, you've pretty much exceeded the power of any given node on our high performance cluster. And by the time you get to 10, you've exceeded the abilities of our cluster. So, you know, you really the exponential growth of these things really does kill you trying to do things fast.
Do you anticipate that being like the way classical computers have developed and different architectures where you might like write your compiler on this architecture for this new chip and then eventually be able to bootstrap it?
Yeah,
So
that's
that
almost
eventually
definitely.
it's working on
Yeah, that's
everything's on
almost
the
definitely
quantum.
how it's gonna be. I mean, our compiling algorithm, when we come up with it, is going to end up being a classical algorithm. That's going to, compile your quantum code to run on the quantum.
So going back to that slide where you were describing the concept. And,
The walk.
yeah, so that slide. So in this instance, that like, when we're looking at like a circuit satisfiability. And I'm assuming of if there are advantages in this case. Is it possible to say that quantum algorithms will have an advantage in any end?
No, well, we don't believe so. We have an advantage, like Boolean, Boolean satisfiability, let's say it's 3 sets, so it's actually NP complete. You can demonstrate an exponential advantage using a quantum walk for solving Boolean satisfiability. But the way it comes about is basically by biasing towards the hard instances. Sorry, the instances where you get an advantage that is large. It's not a really natural exponential advantage, and it's in a weird expected runtime, like not worst case runtime, but expected runtime setting. So in short, you're not going to solve the whole class. And, we don't expect, for reasons that you would need to ask a real complexity theorist about, that we can get a quantum computer to solve NP, complete problems, because that would, I believe, collapse the entire polynomial hierarchy. So, that's like kind of a limit. We don't think that's going to happen, but that doesn't mean you can't still get advantages on those particular. You can still definitely get advantage.
So basically, like you can get advantages only in certain instances when you set.
Not in certain. I'm out of time, so I'm very out of time. So let me